Okay, it seems everything works fine. If you can't see me, okay, I'm here. Okay, so welcome again to our Tuesday seminars at the University of Warsaw Astronomical Observatory. And today our speaker is from Open University in the UK. It's Ulrich Kolb, whom I've known for almost 10 years or so. We've been collaborating on various projects, including robotic telescopes, and Ulrich is going to tell us a few words about their fantastic project. Ulrich is a professor of astronomy at Open University in the UK. He studied in Germany, and then he worked in the US and the UK as well. And he's also involved in Plato, as I understand, and is also a very involved in the didactics and education of astronomy, which is of interest for us, I believe, very much here as well. Ulrich, please tell us about your robotic telescopes and asteroids observations.
Thank you very much. Thank you for the invitation and for the kind words to begin with, and welcome everyone. So I will spend the next 45 minutes or hour to tell you a little bit about our ventures into robotic telescopes, small aperture robotic telescopes and their deployment. And the specific deployment I would like to highlight today is about asteroids and more specifically phase curves of asteroids and what we can learn from them. The work I present is largely done by my brilliant PhD student Sam Jackson, and the brains behind the asteroid science is by Simon Green and Ben Rositis. I will show you more about those people in a little while, but the first part of my talk is dedicated to the instruments and the setup we have, just to give you an overview of where we are, what we are using, why we are using it, and what the pitfalls were perhaps on the way. And I will put this into a wider context of the setup at the Open Universities for remote experiments. But for this, let me just start the slideshow. And I walk through the show. So let me, as I said, introduce to you our observatory. It's called the Open Science Observatories, and it's located in Tenerife at the Observatory del Teide, which I'm sure many of you will know, which is nicely located in the neighborhood of this beautiful volcano, Teide Mountain, and combines quite a lot of different facilities, including solar telescopes and robotic nighttime telescopes. Tenerife is part of the Canary Islands, and of course, most of you will know the neighboring islands facilities, perhaps better than Tenerife's, on La Palma. That's the island highlighted here, where you have, small and large telescopes starting from the Grand Tican and going over the WHT and other famous smaller facilities, including the old Super WASP, worked out from by Warwick University. So Tenerife, the site, is actually almost identical in its conditions to La Palma. It has almost to the meter the same height above sea level, is in the same way as La Palma above what they call the Sea of Clouds, as can be seen here in the background of our two domes. So we have two domes here, Pirate and Coast, they're called, and has similar seeing, sub-arc seconds often. And the main difference is at night near the horizon. Tenerife is much more populated than La Palma. There is no protection, light protection in force such as for La Palma. So observations at higher air mass suffer from a degrading background quality, but otherwise it's identical. So even to the extent that when the volcano on La Palma gave us such grief over the last months, fortunately or luckily, this is now extinct. We could see it at the horizon. So in this picture, it would have been about there. This is La Palma in the background, and the volcano could indeed be seen from Tenerife. And occasionally, the ash cloud was above Tenerife, even though there was no real ash fallout, which would have damaged any equipment. So we were much less affected in Tenerife compared to La Palma during this period over the last months. Our facilities then are, just to give you the specs, as you must have, in Barder Planetarium, all sky clamshell domes, 4 meter and 3 meter wide. We have basically plane wave CDKs, astrographs, a 24-inch mirror and a 17-inch mirror. The instrumentation is exclusively photometry, so there's a set of photometric filters, and the camera is of the type is a Finger Lakes camera, giving a field of view here of 30 arc minutes or so and 40 arc minutes there, with a pixel scale of just below 1 pixel per arc second. Sorry, it should be arc second per pixel, of course. So these are essentially off-the-shelf components, and the whole ethos behind our facilities was to create what I would call an affordable observatory, which is as autonomous and robotic as possible, but still maintains the ability for us to use them in an interactive way, and for, you know, on a limited budget. This is only possible in retrospect now if you pick the right partners and if you make use of knowledge acquired by others in this domain. And I'm really very happy to say that the partners we picked and still collaborate with very productively are Barder Planetarium on the one hand as the main supplier of the hardware, but also on the basically the team helping to build it on site, construct it on site, as well as anything software goes, software control, the Sibylla Technologies, which I'm sure some of you know, the Polish-based company. So in terms of how do we control and access this, there are 3 modes, and they span the range from a completely autonomous Q-scheduled working. This facility can run by itself, completely left to its own devices for days, weeks, months, if we're lucky, on end, fed by a scheduler, which is sort of used by scientists to feed in their observing requests. On the other hand, we can also use it in a interactive real-time direct control mode, say for presentations or for students who have not yet had the benefit of a live observing session on a real telescope. So the ABOT, Sibylla's control tool user interface, graphical user interface for direct control, is what we deploy for our distance learning students. And I should have mentioned the Open University, of course, is a distance teaching university. So all of our students are remote learners, have been even before the pandemic. And so we take great care to supply meaningful activities and tailor-made resources for this audience, for this kind of student audience. And we found that this user interface here is perfect to deliver this. On the other hand, the scheduler also has, in this case, a simple-to-use interface for scientific users, for research use, or for more advanced student use, for project use, say, master's projects, for instance. You feed in your requests and the scheduler by itself works out when to schedule it and interleaves it with other requests as and when it's best for in terms of observing time and observing conditions. We have a third mode to talk to our telescope, and this is really tailored for the amateur user, the not advanced amateurs, but the beginners. And the website there is called telescope.org, so feel free to browse this after the event, where you can essentially enroll in a free Open University course to give you first steps towards understanding the night sky and using a remote telescope. And you can feed in this very intuitive template observing requests. And this course is completely free and is built on telescope.org, which I should acknowledge we bought from the original Bradford Robotic Telescope project, which designed this and has been in operation at TADI for decades. And of course, now no longer in existence, the Open Science Observatories can be seen as the new Bradford Robotic Telescope. Right. What do we do with the telescopes when they're not used for teaching and for these kind of outreach or amateur type activities? And we use it in terms of research use for PhD projects, but also collaborative projects with other institutions, essentially for the monitoring and follow-up of certain events, such as transients. We, for a time, followed up gravitational wave alerts. As Lukas will know, we were part of the Gaia Science Alert follow-up group for microlensing events, for instance. Currently, we are focusing more on transiting exoplanets, and we work towards helping the sample for the Ariel mission to prepare and refine the sample for the Ariel mission and to pin down the timings of these transits, the all-important transits Ariel, the satellite observatory, will monitor once launched in 8 years, 6 to 8 years. However, we also now have started and have been doing for 2 years, probably 1.5 years, a new campaign to monitor near-Earth asteroids to study the variability of their phase curves. And that's really the subject of the second half of this talk. We are involved in also satellite tracking and space surveying campaigns jointly with similar technologies, but prior to this, for other customers, in quotation marks. So we deal indirectly or directly with POLSA, ESA, and EU campaigns for certain periods, so we can track satellites to good effect. And then, of course, oops, I was too fast. We have a deployment, hopefully this is now stable, of this for physics lab courses at the OU in the first instance, but since COVID, as a mitigation of the disruption to higher education in the UK, we rented out facilities such as ours to other universities who use them for their own students as a replacement for face-to-face labs. And for instance, Edinburgh University have used Pirate, our large telescope, for their lab course twice now. Okay, and then of course we also show it off at public engagement activities. This is just before I show you a bit wider the Open STEM Labs initiatives of the OU, which is remote experiments brought to distance learners. The work we do, or an advertisement for the work we do for exoplanets. There is this beautiful project called ExoClock. If you haven't looked it up, please do. This is something I can recommend to anyone who has a good enough instrument, perhaps at home or privately, or at universities, to monitor transits of exoplanets. It's not really difficult to do, and depending on the precision, photometric precision you reach, you can make more or less important contributions to monitoring those exoplanets Ariel will finally target. And this is just one example of a very quickly obtained light curve with Pirate at the end of last year, and analyzed or processed with a software, which again is freely available and easy to use and intuitive to use for the amateurs who take part in this project. It's called I can't see the screen there. HOPS is the software, right? So that's just something I can recommend, and we are getting more into with our telescopes going forward. So how does this sit within the wider setup of the Open University's remit to bring practical science or practical STEM subjects, so technology, engineering and mathematics, as well as science, to our university students who are remote learners. And the Open Science Observatories is just one element here. There are other similar entities under the umbrella of what is called the Open STEM Labs. And for instance, the Open Engineering Labs, the Open Computing Lab, the Open Health Laboratory. And initially there was the Open Science Laboratory, which had all of these components and is now being distributed to these more specialized entities. And what does that mean in practice? We have a suite of remote experiments, all accessible via a unique interface or landing page, which sort of distributes students out to these different bookable experiments with real-time access. And of course, Pirate and Coast is one. And then there is on this side, there is an electron microscope, for instance, a scanning electron microscope, which students can access and get data from, or this is some automated titration going on for measuring the acidity of, well, acids, or on a slightly different end, very much related to space activities. We have a remote controlled Mars rover, which is obviously a toy rover, but embedded in a Mars yard with realistic looking Mars landscapes. And that's used by students who control this rover via remote commands, much in the same way as the real rover on Mars is being controlled. And there is a built-in delay when we teach them to do this between the commands and the actions, and they sort of can see what the cameras on the rover can see, but not a picture like this where they can see where the rover really is. So it is as realistic a simulation as we can make it for students of this, in this case, master's module on space science, what it takes to control and usefully deploy a Mars rover for scientific investigations. On the other hand, and for very simple apparatus, this is a pendulum which can be forced in a certain way and produce all sorts of resonances or chaotic or periodic behavior, and students can observe this. Or this is an instrument which is producing signals modulated when this disk spins, because it blocks out or lets through certain laser light, I believe, which is then registered, and you can do a Fourier signal analysis on the outcome. Or here is a cylinder which is filled with oil, and can study the reaction of it to different pressure, a different pressure in the oil, and study the strain on the material. So it has a range of facilities from the very expensive end to the very simple end, but all remotely accessible. And another one which is relevant for the astronomy part of the curriculum is a radio dish, a 3-meter radio dish, which is situated in our main campus in Walton Hall in Milton Keynes in the UK, and has, in this case, a very intuitive, simple interface for students to study the 21 centimeter emission from the Milky Way and basically set up a rotation curve of the galaxy and a project built around it for dark matter content of the galaxy. All of this is done in order to provide practical experience for students in an inclusive way. Students can access this at any time, anyone, so there's no need to go to a lab. It is for remote users in any part of the country, in any circumstances, as long as they are online in the internet. It's suitable for all sorts of modes to optimize the teaching of practical science. So it allows individual as well as group working, and it is possible to have interactive and collaborative student-led or tutor-led inquiries. It is very versatile in that sense. And most of all, it is, as far as the remote experiments are concerned, absolutely authentic. There are real data. These are not fake data. These are not simplified data. These are real data coming in at real time. They are completely authentic. the instruments are, even the simple ones are bespoke to deliver what is asked for them. All of them are industrial grade and some research grade, such as the telescopes. The initiative dates back quite a few years, predates the pandemic and came to its own during the pandemic. So it was a vision of what was to come. It is now actually used by an awful lot of students, about 10,000 users per year, and this increased by 50% during the peak of the pandemic. So it's a big enterprise of the Open University, of the STEM faculty, and we are fortunate that the observatories are a main part of this. So let me come to the science and the asteroid phase curves, because that's what you would like to hear about. And my collaborators, as I said at the beginning, are Sam Jackson, who is now in his third year and extremely productive. And many of the slides I show subsequently will have been made by him. You will see the different style of slides, it gives it away. And the brains behind the science certainly are Simon Green, who is, has a long experience in planetary science and astrophysics, and Ben Rositis, who is a research fellow and is closely involved in a PI function at the OSIRIS-REx mission, the asteroid sample return mission to the asteroid Bennu. Well then, asteroids, and here are a few asteroids seen from, what they really look like. They come in all shapes and sizes, and some of them we have close images of, and others we have radar data on. They clearly are rocky bodies dating back to the beginning of the solar system, and hence can tell us potentially something about the conditions present when the solar system formed, which is why we are so keen to study them more. However, many of them will have undergone a lot of evolution since the formation, and then therefore likewise we will need to understand, if we study them and want to make conclusions about conditions at the beginning of the solar system, we need to understand the way they evolved. The number is enormous. There's more than 1 million known, and this figure quoted here is now almost a year old, so it's probably much larger now, or large now anyway. However, the total mass, and that's something I find quite astounding, of all these asteroids taken together is still less than the mass of the moon. Why would you study them? As I said, we want to understand evolutionary processes, and one very interesting process is that their composition and structure and changes in those may drive various processes, both internal to these asteroids, but even more so externally visible ones, because they may change the orbit of these. And more specifically, if you look on the left-hand side, this is, and you will have seen this perhaps many times, this plots the number of asteroids against their semi-major axes, and obviously they sort of, most of them sit between 2 and 3 AU. However, there are these very pronounced gaps in the distribution, and these are resonance gaps between the orbits at these semi-major axes and Jupiter, and essentially asteroids which may be finding themselves at these gap semi-major axes will eventually be perturbed in such a way that they can be changing their orbit to come closer to the sun, become more elliptic, and will be transferring into what is then called near-Earth asteroid. And the asteroids, even those asteroids sitting in what looks like the safe zone of semi-major axes, may eventually migrate into the resonance zone if they are subject to these thermally and radiation-induced forces. So near-Earth asteroids, asteroids which come closer to Earth than those in these main belt, in the main belt, are of course of interest because they potentially risk the safety of Earth if there is possibly a collision expected. And we all know that there is work going on relating to planetary defense, and there are movies about it and so on and so forth. It is a real risk, and it is quite appropriate to study what could or should be done if there were a asteroid and collision curve. Near-Earth asteroids in any way are interesting for us because they come closer, we can study them better. And finally, I should say, there is also, as far as asteroids concerned, the possibility in future, or perhaps not so distant future, to make use of resources on the asteroids. And we have, missions eating asteroid material and bringing it back to Earth. So this is not some science fiction. We are already quite near to this. How do we study them, and what's this got to do with robotic telescopes? So asteroids move around the sun as well as the Earth is moving around the sun. And we have what we call a phase curve variation of the brightness of the asteroid as a result. The asteroid will, as it moves about, have a certain distance r from the sun and a certain distance delta from the Earth. And obviously, the further away from either it is, the fainter it will appear. And likewise, the variation of its brightness will also exist if the angle between the sun and the Earth, as seen from the asteroid, changes when both orbit the sun. These are the phase angle variations. And if you want an equation written down, then the V magnitude of an asteroid will depend on R and delta and alpha. And you can now normalize this to obtain what in astronomical terms would be the absolute magnitude of a star, a distant corrected magnitude, by removing the log of R times delta, essentially, and convert this to a standardized V at distance from the sun of 1 AU and from the Earth of 1 AU, and you're left with only the variation of a sort of corrected or calibrated V magnitude as a function of angle alpha. And that's what's called the phase curve. So the phase curve looks at how does the V magnitude vary as a function of alpha if the asteroid is placed at a standardized angle. At a standardized distance r and delta, but varies in alpha. There is a further rotation, and this is, of course, because of the rotation, further variation, I wanted to say, because of rotation. And hopefully the next slide shows this, but it's stuck. There we are, rotational variation. So these asteroids, and they are not always nice and spherical, rotate. And depending on what shape is facing the observer and what the surface is made up from, you will see different reflected, re-emitted light, so different light shining back to the observer. And this is a real example of a light curve of this satellite, of this asteroid, which produces this peaked curve. There are about 5,000 asteroids with well-defined spin periods, and about half of those have shapes derived. So again, this is a complication in the business. Let's see. Next slide. Which brings me to phase angle variations. So if we take out the variation due to the distance and take out the variation due to the rotation, what we are left with is the variation in brightness as the asteroid moves about due to the orientation, the relative orientation of Earth and Sun with respect to the asteroid. And this is expressed in these phase curves, where the phase angle 0 means this is in opposition. So the asteroid sees the Earth and the Sun lined up and goes to larger values, such as 90 degrees, where they are, in right angles to each other. And the typical shape of the phase curve is as indicated, so it's roughly linear, but has an interesting, in many cases, upturn near 0, the opposition effect, where the self-shadowing and becomes apparent, or the disappearance of the self-shadowing becomes apparent, and the backscatter might be particularly effective. So the conventional wisdom here is that the phase curve is determined by the physics of the surface, so the roughness of the surface, the composition of the surface, the cratering of the surface. And so this tells you, the phase curve tells you something about the conditions on the surface of the asteroid. And these are real examples, the Apollo asteroid, and funny enough, the moon is shown here as well. The dots are measurements, while the curve here is a semi-analytical model, H and G, one which I will use again later on. The H is an interesting one because it measures the H value, essentially measures the visual magnitude this object would have at 0 degrees in this standardized 1 AU distance from both Sun and Earth. So it's a sort of not real distance, but it's one that's normalized. So why is this interesting? I think I said this because it allows one in principle to derive physical properties of the asteroid, such as the diameter or albedo, and it may also be used to a classification of the asteroid because it tells us something about the surface of it as such. Right, so let's go to the next slide. What is it we have been doing? When Sam started his project, he was first of all trying to establish if there's a large enough number of near-Earth asteroids that are accessible to us with the telescopes at our disposal. When he started, Pirate existed in a somewhat different configuration to the one I introduced. The one I introduced is what we call Pirate Mark IV, and this is in existence since last summer. Before that, we had what we term Pirate Mark III, and this was essentially an instrument which now is coast. So it is or was a 17-inch mirror with the current camera, and the 17-inch mirror essentially limited, so we thought, us to asteroids that are brighter than 17th magnitude, and hence this campaign and sample set Sam set up was looking for asteroids that were visible, observable from TAD and became brighter than 17th magnitude near their opposition, where the phase angle also covered an interesting range of parameters. And as you can see, this is one example. This one had multiple apparitions at different times, 3 times, and covered, certainly the middle one, a very interesting range near 0 up to 60, 70 degrees. The tracking rate, or rather the speed with which these moved, and also the speed which we can track, and I'll come to this a little later with the setup we have, is of order a few arc seconds per minute, up to perhaps 20. If we pushed it, certainly not more than 100, but realistically, the sample we are observing sit well below 20 arc seconds per minute in movement. So just to give you an idea. Right, so let's go to the next. What I'm going to tell you now is the observing strategy and a few technical details of the setup we've created for doing these observations, for conducting this campaign. And this is actually published in last year's PASP paper by Jackson et al. So you can read it up there. The observing strategy was that we always observed our asteroids in R and V filter. So our filters on Pirate are Johnson filters. And this allowed us to obtain the instrumental color of the asteroid and stars, bearing in mind that, of course, R and V have to be taken in subsequent frames. So there's some interpolation necessary to work out the color. There was a need to implement differential tracking. So it's not sidereally tracked, but the method is to track the asteroid itself. Now I'm slightly confused because I'm sure I had a different slide. Can I try the next one to see if this perhaps has, yep, that's the same slide, first half off, and it has an image. So it's what I just said, the differential tracking is necessary to boost the signal to noise of the asteroid, which is the faint object. If you were to sidereally track, you get your stars nice and round and faint stars, but the asteroid whizzes through and therefore wastes its photons on a streak rather than in a point where it could have a much better signal. And so what we therefore do for these faint objects is to track the asteroid and allow the stars to be trailed. The particular approach taken is that we work out a mean or average rate for the asteroid while it crosses the field of view, and then keep the field of view the same by tracking the asteroid a tiny bit for about as much as 100 pixel lengths in star trails, and then resetting the telescope to the same position and reacquiring the asteroid as a point. And so therefore, the kind of animations you may see coming out of Pirate when it observes asteroids are like this, where you have a set of trailed stars and a point-like asteroid going through the field of view in this way, okay? So the advantage of doing it this way is there is a stable field of trailed stars, which allows one to do a good photometry on this particular field. Of course, once the asteroid is out of the field of view, you would have to move to a different field. And in practice, what we do is in one night, at any given night, we do one such field. That's enough to establish a phase curve, which is a long-term monitoring program rather than a detailed sitting on the asteroid for many hours on end. Okay. So next one. And by the way, there is an asteroid called Open Uni, and it has an interesting number, which is has significance for Open University people, because the 23rd of April, 1969 was the OU's charter day. So basically when the OU came into being as a university, and this asteroid was named because we have quite active and well-known asteroid researchers at the OU. So what happens if, how is this fed into the telescope? There's an automated, if you like, program setup tool. There's a query going on of the Horizons data base, ephemeris system to find the mean RA and declination of suitable asteroids. This determines the program length, determines what the exposure time is, make sure that the tracking error from using a mean rather than permanently adjusted tracking rate doesn't get larger than the seeing, and keeps the exposure time to limits as desired. And the outcome of this is something like this. Once in place, once the data are there and transferred to our servers at the OU, there's a pipeline in place which then plate solves the data set, all frames, and establishes photometry. And the code we use, the tool we use is source extractor with elliptical apertures, and they allow us to do photometry on the stars, even though they are trailed. So there are elliptical apertures, and at the same time, the same setup allows you to do the photometry on the asteroid, because that's, even though that's circular, it's still part of, you know, an ellipse in this sense. The pipeline auto detects the asteroid from its known RN deck after it queries in real time, again, the Horizons database, and then engages in ensemble photometry using the trailed stars as the backbone over the number of frames where the asteroid's going through, and obtains the relative light curve in the instrumental R and V Johnsons and the color for the asteroid. To transfer this, and this is absolutely vital if you do light curves for, in fact, phase curves for asteroids, you have to have the actual magnitude. You need to transfer it to the true magnitude. You need to calibrate it to the true system, because the next observation, the next night, is a different star field. The same asteroid, but you have a completely different set of comparison stars. And so you need to put it to an absolute magnitude scale. Otherwise, you can't do a long-term, even relative light curve. That's no longer possible by virtue of this moving object. So the solution we implemented, and this is really Sam's work, is to use the existing pan-stars catalog, and the pipeline queries the pan-stars in real time via API to obtain the RP1 and GP1 magnitudes for all the stars in the field, and uses those to transform instrumental magnitude and color into the actually, and that's the main outcome, the true Johnson V-band light curve. And the term which, you know, comes out of this process, rather convoluted process, is that the V magnitude we want is obviously given by the instrumental R magnitude, but then terms, linear and quadratic terms of the instrumental color and certain constants. And these constants include constants such as 0 points, which have to be determined again new each night, and also gradients, which of course remain fixed. And this is effectively the same as if you do absolute photometry on a star field, but a little more complicated because it's on a moving asteroid with trailed stars. And the next, sorry, wrong way. The next slide, hopefully, gives you just a sense of the quality of the calibration relations we have. So the one which is beautifully linear is the color transformation between instrumental V minus R and the pan-stars G minus R. And the color term gradient for which is also used between color G minus R for pan-stars versus R, effectively is a very small one, has a apparently larger scatter. So this is set up from an abundance of stars and a multitude of frames, many thousands and thousands and thousands, and is sort of recalculated a few times, but otherwise fixed and can be reproduced very nicely over and over again. And the outcome then is something like this. So this is one particular asteroid, a near-Earth asteroid, this particular number. And what we show here is the rotation curve assembled by folding with the correct rotation phase the different branches that were observed during these different observing nights. And these are in fact 35 nights, so 35 different observations, a total of 118 hours with the smaller period. These are the calibrated V magnitude, so the true V magnitude of the asteroid. So this is not phase curve corrected, that's just the asteroid as such. The period is about 60 hours, and you can see that despite all the difficulties of stitching together these different parts, there is a very nice light curve emerging, and all data are shown, so even those which didn't come out to fit perfectly, and it is quite likely that in this data set, for instance, the calibration of the V magnitude didn't work as well, and this is the most likely explanation here, because as you can see, these are not as many data points, so this was a night where conditions probably allowed only a few data to be taken, as opposed to the much longer data set where the 0 points have been determined much more to a much higher accuracy. Right, so the rotation curve is important because for the business of the long-term behavior and the phase curve, which we are really after, you need to correct for the rotation. You have to sort of produce a rotationally averaged magnitude and then plot it as a function of this phase. And so let's just go to the next slide, and that's what's shown here. These are for the same asteroid as just before, this time shown the V magnitude at 1, 1, so 1 AU from the Earth, 1 AU from the Sun, versus angle alpha for the same data set. And the angle is between 0 and 50. And well, there is sort of this one semi-analytic fit. This just demonstrates that an instrument like ours at the time was capable of producing a very sensible looking phase curve in this way. And so these data points are rotationally averaged, okay, which obviously introduces a further photometric uncertainty in the game. Right. In the last part of my talk then, oops, I seem to have a companion here, so excuse this. In the last part of my talk, I will speak about a new study, which is a paper we are working on, and it is in advanced stages of preparation, but not yet submitted. I will tell you anyway what this is about. And it's again a paper led by Sam, but also with Ben and Simon as the brain behind it, and collaborators from Kent, who all are asteroid researchers. And it is about aspect changes and how they impact on phase curves. So the conventional wisdom is that phase curves, as the one I showed you, depend solely on the surface properties, on the scattering properties of the object we are looking at and the size of it. And this is how in the literature phase curves have been used over the years and used to interpret or classify or estimate the emerging brightness of asteroids as they come round and nearer to us. What we did is we used a data set on one particular asteroid, this one, whoops, too quick, 99 AP10, over a period between July 2020 and January 21, to show that actually life isn't that simple, and object shape, rotation pole orientation, and viewing geometry over the apparition also has an effect. And this effect can't be neglected. And if it is, and everything is essentially averaged out, there is then an additional uncertainty in any physical properties that people would like to derive from the phase curve. And potentially, this could also lead to misleading interpretations. So that's, in a nutshell, the outcome of this. But I'll show you a few slides, how we got there and what it means. So the satellite was observed, sorry, I keep saying satellite, the asteroid was observed for 38 nights with still Pirate Mark III, so the smaller one, for a total of 200 or so hours. But this was supplemented by companion data by the Palmer Divide Observatories, published here in Warren and Stevens 21. At this stage, I can't quite say how many data there are. Feel free to look it up. I should also warn you that in the team, I'm certainly not the asteroid specialist. So I'm not as close to those data and to the science as perhaps you would like it to be, but it's my way of explaining what we did. So let's see how you fare with this. So these data were used to construct what you see on the screen, a shape model of this particular asteroid. And this shape model is obtained with a particular software, ConvexInf, and obviously, as you can see, is using a number of facets which are given certain emission profiles or properties or reflecting properties according to a model. And we are using a model for this, which is well known in the literature and has plenty of parameters to play with, but was set to a sort of standard set of parameters. It's the Hapke model. And the light curves, these many light curves, 38 light curves from us, plus possibly a similar number of light curves by the companion observations, were simultaneously fitted by this model asteroid in order to minimize the deviations from all light curves. So this is a fairly advanced set of simulations with, of course, not necessarily a perfectly unique solution, but with one which produced overall the best fitting outcome. And that's the one shown here from different sides. So you can get a sort of sense of the shape of this asteroid. And particularly the best fit one comes out with pole coordinates in elliptical coordinates, such as the ones given here. So 36 degrees off the ecliptic plane. It's therefore the rotational axis does not sit perpendicular to the ecliptic in this case at all. And the rotation period is about 8 hours. Okay, so in the next slide, see this again. And one example light curve, because I was saying the light curve for a particular night here is shown via data points, and it obviously is producing a very sensible fit, this model, to this light curve, but not just to this, but any data available of the whole apparition. And that's all input into this shape model. Okay, I'm sorry to move back and forth. That's some weakness of my mouse setup, apparently. So this is the shape model which optimized the fit. It has, as you can see, a sharpish bottom, which is possibly an artifact due to the limited coverage when this was particularly pointing towards the observer had a major impact. But it is otherwise quite similar to other, what are known spinning top asteroids. So it is quite sensible and not, not to be dismissed. By the way, the code setup used obviously was verified in different settings, and this is just one verification demonstration for this rather more famous asteroid Bennu, which was visited by the OSIRIS-REx mission recently. This is the phase curve of that asteroid, is published by Hergenrother et al. 2013, and the very same shape model software setup was used with Hapke model data or parameter set to produce this fitting, properly fitting phase curve for this. These are not pirate data. Okay. And so this is effectively the outcome of this study, and also essentially the last slide I have before I summarize. And the aspect changes along the trajectory of the asteroid when it transverses this range of phase angles. These are, again, the asteroid observed by Pirate, and these are the Pirate data for the phase curve. What the model shows is that the phase curve evolves for the different phases, if you allow me to say it this way, during the apparition. The color code is a time axis. So this spans 175 days through the different colors, and allows you to see that the trajectory, the observed apparition, begins here, and then the asteroid moved closer to smaller phase angles, then turned around, moved away to larger angles, but turned around again and moved back in to end in the yellow data cloud, which is also zoomed in and magnified here. And so what you can see from the shape model phase curve fit is that the different branches of the asteroid's apparition do not coincide. And there is in particular a very real visible offset between the branch when the asteroid is moving away in phase to when it returns. And we spent a good deal of time to establish that this is a real difference and not just, mimicked by photometric noise where perhaps certain data points sit above or below expectations. It is a very real effect. And it is one, this study, which is being prepared, is investigating with models, fake asteroids, simplified models, to see what the width of variation in parameter space is in terms of phase curve variation, depending on viewing geometry and orientation of the rotation axis. And you can have very extreme cases where the phase curves of going in and out branches are wildly different. And so this is a moderately strong case. There will be cases where they are much more pronounced. And the main lesson from and outcome from this is that in order to interpret phase curves, it is important to look at their full time evolution and not to just sum over or average over multiple apparitions or different parts of an apparition where the same phase angle range is being crossed. That shouldn't be done because it will then give a different model fit to the phase curve and a different interpretation for, say, the surface properties of this asteroid. And what's more, by doing it in this timely resolved way, you learn more details about the shape, orientation, and surface properties of asteroids at large. And that's the lesson I want you to take from this study. And I would like to summarize. And what I tried to convey today is this. The Open University, I demonstrated to you, has what is called the Open STEM Labs initiative, which brings essentially authentic laboratory science to distance learners. And the Open Science Observatory is really annoying that this jumps forward when it shouldn't. It was my last slide, so bear with me. Seems to be stuck now on this movie. Here we are. Let's hope it stays here. I don't touch the mouse for the time being. The Open Science Observatories are, if I like to say, the astronomy wing of the Open STEM Labs. And basically what I showed you today, I hope demonstrates the usefulness, as I call it here, the prowess of a small multi-use facility. So our small telescopes are not dedicated facilities that are tailored to do one piece of science very well. They are there to do a lot of things, and it's still possible to conduct research with real scientific value, as I hope I showed, in long-term monitoring tasks with facilities such as this. And the example I showed was phase curves for asteroids, where we have developed, as it were, an observing routine and data analysis pipeline for near-Earth asteroids. And we have found or demonstrated that phase curves show a dependence, which so far has been neglected largely in the literature, on the shape, the rotation, pole orientation, and viewing geometry. And so the interpretation is harder than perhaps people thought so far, but also richer. And with this, I stop. And I really wanted to show this at the end. You've seen it before. It's just a nighttime, scene of the observatories busy doing their thing under the skies of Tenerife. So thank you for listening.
Thank you very much. Thank you, Ulrich. If there are any questions here in the audience, please do come forward, because our microphone is not that sensitive. And I do encourage people to ask questions here first. Maya, please come forward. So then
Hi.
Hello.
Thank you. Sorry, where's the light? It's here.
yes.
Okay.
Speak to them.
Okay. So hello, thank you for the presentation. And I'm wondering, are you thinking about extending the near-Earth asteroids studies so that you can, for example, monitor more objects and possibly creating some sort of an estimate if there's really anything near Earth that could, for example, impact us or something like that? Since you have mentioned it is really a risk.
It is a real risk, indeed. Certainly we will widen our campaign, because, as I indicated, we have now the large telescope. We expanded the 17-inch to the 24-inch, and also have the second facility available in principle. So we certainly intend to widen the sample to observe, but none of these observations and the whole campaign is not really about finding new objects. So all of these asteroids we observe are already known, and arguably, conceivably, the detection of potentially dangerous asteroids is most useful if it is accomplished when they are as faint as possible. So hopefully fainter than we can deliver. In practice, many of them slip through the net and may be detected by smaller facilities when they are already quite bright, quite near, quite dangerous. So while we don't rule out serendipitous discoveries, we are at the moment not intending to engage in a sort of survey type of activity which would specifically search for those. Even though if at a future time there is a proposal which would make us, say, part of a wider network of telescopes to help in such a survey, we could do that. But again, we are certainly limited in terms of magnitude depth, how faint we can go. So that would be my answer. We will increase the sample to somewhat fainter systems, but the advantage is we will increase the phase angle range accessible to us, and making perhaps the phase curve variations more visible, and can investigate them more systematically. But most of this work will be done on known, established, or at least known near-Earth asteroids rather than new ones.
Okay, thank you.
Thank you. If there are questions, Radek is raising his Zoom hand. Please, Radek.
Hi, thank you very much for a nice talk. So I have two questions. So first of all, you showed the light curve on slide 24, the phased light curve, and some trends could be visible that this fit that is shown does not fit all the data very well.
Correct.
The cause of these differences is physical, or these are the problems with aligning different data sets?
Yeah, so I think there's two or three things hidden behind this. One is, as I was indicating during the talk, cases like this where a fairly short observational data set, where the reason it's short is always it had to be interrupted for some reason, such as bad weather, didn't allow a proper calibration of the magnitude on the absolute scale. And so my most likely explanation for now, without having had the chance to look into detail what this data set, what is wrong with this data set, is that there is an offset because of a not properly conducted 0-point calibration, for instance. So that would be my most likely explanation for this. This one does look more like it's at the wrong rotational phase, because this is a very well-defined branch. And you could imagine if this is moved to a different phase, it much better fits the overall shape. I don't know if this is the case. One of the downsides of running campaigns like this on not just one target, but 20 or so targets, producing large numbers of data sets, is that most of the time we rely on an automated pipeline. And the output you see here is largely output of the automated pipeline. If you wish to go back and interrogate individual data sets individually to see what's going wrong, that's a lot more time consuming, which is not something we haven't had really the time to do. But on this occasion, we would certainly want to. Lastly, the other thing one needs to be aware of is that these these data sets span a long period of time of half a year, essentially. And during this period, as we have seen, the asteroid transverses quite a path in phase angle. So the viewing geometry changes. So the whole discovery I was explaining at the end is hidden in this plot as well. Because the viewing geometry changes, you can't simply compare the different branches of the rotation curve to each other, because you look slightly different at the asteroid and the orientation of the rotation axis. So there ought to be a main compensation of the viewing geometry, even in this plot, which at the time for this plot, I don't think was done, or if it was, only in a simplified way. So some of the scatter you see here is sort of has a physical origin, which is this phase curve change with time.
Okay.
And some is certainly artifacts because of the data analysis or incomplete data sets.
Okay, thank you. So 3 slides later, you showed the shape of the asteroid. So
this one?
Yes. My question is if you have uncertainties of the shape parameters or the pole coordinates, or it's just best fitting?
Oh, yes, this is the best fitting one. We do have uncertainties, which not in this slide set, but this is, yeah, I can't quote you those now. Maybe I can just have, let me see if I find a quick, yeah, I wonder how I could show this. I could exit my screen share and share different. Shall we try this? I exit my screen share, stop share, and share again. Can you see this? So this is basically the paper draft we are working with. And this is the pole scan plane of latitude and longitude with chi-squared values of fit. And as you can see, this is by no means unique, simple or otherwise. What we can say is that the deepest minimum, so to speak, is here. That's the values I quoted to you, but these uncertainties depends on how you want to do it. So these lines here are 1, 5, and 10% uncertainty contours, and the best way of quoting this would be lambda is 8 plus or minus 4 degrees, beta is minus 36 plus or minus 2 degrees, and so on. But there's at least one other local minimum. This is the deepest and arguably the best fit one. So there's lots of uncertainty built in, and there's a way to estimate this rigorously as well.
Okay, I will step in here. Thank you very much. Thank you for all the questions and the answers. I will just wrap the discussion here with a comment that I hope that at some point soon you will also have in your curriculum black hole finding with microlensing. So we will be very happy to collaborate on this, get back to what we've been 10 years ago. I'm very happy to talk more about this. I think your students would be also interested in this kind of topic.
I imagine they would be, yes. I'd be keen to revisit this. And yeah, I mean, clearly, ever since Meredith, who I believe you know from various conferences, completed his PhD and left to his postdoc elsewhere. This area of investigation with our instruments and any attempt to include it in perhaps even the curriculum sort of was on ice. But it's certainly an area I have fond memories of and would like to drive it further. So yes, by all means.
Let's talk about it for sure. Thank you very much, Ulrich. Thank you.
Thank
again.
you.
And thank you all for joining, and I will stop this thing.
Okay, thanks very much.